Monoids, monads, and applicative functors. Repeated software patterns. Now, why would we want to talk about software patterns? Well, in a nutshell, it's this. You have your interface to your class, you have your implementation detail in the private section. What are you going to expose as your public interface? Well, in order to answer the question of what are we going to put in our public interface, we need to figure out what are the fundamental operations. Now, you've probably seen classes, God classes, with hundreds of member functions, but many of those member functions could have been implemented in terms of the other member functions. So what are the fundamental axioms of your type? And then what is the flexibility that you want to be able to provide your user given these fundamental axioms? When you do things in a functional design way, these are critical questions when you're designing your interface. And finally, when you apply some of these functional design patterns, you're going to be able to see how they relate to other classes. These are very powerful generic patterns, and there's a lot of composability with other classes. So, one thing I want to get straight right from the beginning is that functional patterns are not for the users. You don't expose something called the Monadic Bind operation. Why? A user is going to look at that Monadic Bind operation and say, what is this thing? I have no idea what this does. Your interface sucks. Now, that's not saying we shouldn't expose a Monadic Bind operation, but don't call it a Monadic Bind operation. Now, it may be at some point in the future, C++ users everywhere are going to be familiar with category theoretic concepts, and you can call it Monadic Bind, and they're going to understand what it does. But until that point, make sure you use good names. You can use the power of category theory, but you can also get an intuitive UI by making sure that you name your things in a way that your users expect. And one final note, writing generic code is a lot of fun. It's super fun. We're going to have some fun in this talk, but readable code is even more fun. Well, it may not be more fun, but it's better for sure. And certainly for you as software engineering profession, know that this is really important for you. So, a little bit of history about what we're talking about. You've all heard of the language Haskell. Haskell started out as an academic programming language, which is modeled after math. The folks that made Haskell got together and said, hey, we really love math. Wouldn't it be cool if we had a programming language that was basically math as a programming language? And let's see if we can make that efficient somehow. Now, purity is a really big deal in Haskell. This is what separates it from the other languages that were functional at the time, is that they stuck with purity. So what is purity? We're not going to go into too deep detail about purity, but basically a pure function, if you give it the same inputs, you'll get the same output every time, and there are no side effects. So they basically excluded side effects from the language from the very beginning and tried to figure out how far they could take it as a programming language. They used streams as the I/O model, but this was extremely cumbersome. And you couldn't really do powerful things in Haskell when it first came out at Haskell 1.0. So Haskell 1.0 was absolutely a toy language. And that's okay. These are researchers working on theoretical concepts. Practicality wasn't their goal. However, later on, Monads hit the stage, and things started to change. In 1989, Eugenio Moji was looking for ways to describe the meaning of programs in an abstract way. And he discovered that category theory, a branch of mathematics, could be used to model state and exceptions. And that was fine, and a few years later, 1992, Wadler made the key discovery that monads from category theory could be used to express I/O in Haskell. And this was a game changer because this made Haskell actually useful. It was no longer a toy. So category theory becomes popularized in functional programming since. So you'll hear a lot of category theoretic concepts and all this, and it all came back to that 1992 discovery that monads can model I/O in Haskell. Now, category theory. What is this thing? As I mentioned, it's much older than Haskell. The investigation started in 1942 by Eilenberg and Mac Lane. What they were attempting to do was to abstract over various mathematical models. So back in your algebra class, you may have started with a bunch of axioms for math, and you tried to prove out all the other things that we know about mathematics. This was very common at the time, and there are different sets of axioms that you can use in different domains to make varying mathematical models. Category theory was all about figuring out how you can abstract over all the different models. So it was extremely, extremely general, and it made it applicable to many domains, even outside of mathematics. Music theory, for example, is something that has made use of category theory because of its generality. So when we talk about in computer science patterns, usually we're talking about things like factory and singleton and all these other things that are really based on utility. It just seems like something in the toolbox that a lot of people go for frequently, and that's totally cool. But what we're talking about in terms of design patterns is something fundamentally different. We're talking about patterns that are discovered in nature. These are not going away. They are not transitory. These are related to the physical laws of the universe, and they can impact how you design your programs. Now, when you hear words like category, functor, duality, monoid, isomorphisms, etc., all these words are associated with category theory. We're not going to cover all of them. We're only going to look at a few of them, and then you can go on after this talk and do your own investigation and research and discover the wealth of interesting theoretic concepts that can apply to your to your designs. Now, we're going to start taking a look at the first of our category theoretic concepts, which is called a monoid. So a monoid is a type in combination with a binary operation. A type T, some kind of binary operation, which is like a cross with a little circle in it. Now, the binary operation combines the values. Now, in order for a type combined with a binary operation to be considered a monoid, all you have to do is have these two properties. First, that operation needs to be associative. A op B op C is the same thing as doing B op C and then doing A op that at the end of it for every single value. Now also, this type needs to have a special value E such that E op X is the same thing as X op E, which is just X. In other words, it's the identity operation. When you apply it to the operation, you get this almost like an identity function. Does that all make sense to you? Okay, well, let's try to break it down into a simpler example here. So, numeric types, like numbers. All right, we're not doing any programming yet. We're just talking about numbers. We have A plus B plus C. If you do A plus, the parentheses around A plus B first, A plus B plus C is the same thing as A plus B plus C if you put the parentheses around B plus C. Does that make sense? Okay, good. Now, what should be the special value? What do you put plus any number to get that number back?
0.
Yes, exactly, 0. So we have the numeric types, and we have the special value 0, and you put these together with plus, and you get a monoid. All right, now let's see who can take a gander about what the monoid would look like if we had numeric types with multiplication. Well, the first question would be, what is the special value? What do you multiply by any number and get that number back?
You multiply anything by 1 and you get the same thing back.
Yes, exactly. You got it. You got it. That's exactly what it should be. So the numeric types with multiplication are monoids if you look at 1 as the special value and you use just the multiplication operation, which has the property of A times B times C equals A times B times C no matter where you put the parens. Cool. Now, what about an unsigned number with stood max as the operation? Well, if you take a look at that property of, max of max A, B, C is the same thing as max of A, comma, max of B of C. Okay, that totally makes sense. What would be the special value for max with an unsigned? Max of anything in this number gives you the other thing.
0.
Yes, Carmen. Yes, exactly. 0 is the special value in that case. Absolutely. Great. So now we're being able to discover more and more monoids. And let me tell you, monoids are absolutely all over the place. Now, one other question that you might ask is, and I'll leave this for an exercise. Kids, don't give the answer away, because I want the people on the screen to do it. The question is, what is the E value for the float, comma, stood min monoid? All right, you guys in the audience that aren't my kids, please figure this out and think about it. It's actually quite an interesting answer. Now, here's another question. Does stood vector form a monoid with something? Think about it. What would a monoid, if vector were a monoid, what would the operation be?
Concatenation.
Yes, that's exactly right. Basically, with a stood vector, if you have a vector and another vector and you just concatenate their contents, that actually forms a monoid. And what would be the E element for the monoid in that case?
The empty vector.
Correct. Now, what could you do if you had a list or some kind of collection of monoids? What would be some kind of operation that you could do on such a thing, knowing only that it's a monoid?
Squash.
That's right. You squash them. That's the thing about monoids, is that you can basically squash them together, whether you have 0 of them, in which case you produce the E element, or you have a bunch of them. Now we're going to talk about some fancy monoids. Now, stood optional template. A stood optional, which you all know, is either null or it has a value of type T. The question is stood optional a monoid?
Yes, because you're asking.
Yes, it's a monoid. So what would the monoid operation be like?
If it's an optional of a monoid, the optional monoid is a monoid. Use the underlying operation on the optional contents, assuming it has some.
Yes, exactly. A stood optional monoid is a monoid. So if you have a stood optional of a monoid, that is also a monoid. And the way that you do the operation is if the left-hand side is empty, then you choose the right-hand side. If the right-hand side is non-empty, then you use the monoid operation of the left-hand side and the right-hand side. Otherwise, you just choose the left-hand side. In other words, if they both have something in it, you squash the two things on the inside to get your optional monoid. Now, another stood optional monoid would be, for example, this, where you can take, essentially just always prefer the right-hand side. That also would form a monoid. There are a few different ways of doing this, really. So here's a more complex question. Do functions returning some value form a monoid? Functions of the same type that return a monoid are also a monoid. And here's what that function would look like. You essentially have a function called append, which takes in two functions and returns a new function based on the results of the two functions in the input. So it builds a lambda function on the inside that takes in any value a, and the results of that lambda function takes the left-hand side operated to a, monoid operation of the right-hand side operated to a, and squashes those two together. And that's how you can have a function that returns a monoid, that the set of functions which return a monoid actually form a monoid themselves with this kind of operation. And the empty element, of course, is going to be the function which takes in any value and always returns the empty element of the monoid. Let's say you want to search for the n best occurrences of a word in 1,000,000 documents. The key insight here is that an n-heap data structure is a monoid. An n-heap, in case you weren't familiar with it, is basically a list of the best elements, for some definition of best, and according to like their goodness criteria. And you can take n-heaps and combine them together to get other n-heaps. And this is a monoid. You can split documents between your cluster nodes. You send the word to each of your cluster nodes, which has many, many documents. Each cluster node generates its n-heap using internal parallelization, and then each cluster node sends its heap to a collection node. The collection node just joins the heaps using the monadic operation. key insights here that we're getting about monoids. They scale very well. They compose via functions and optional and other things. So remember when we talked about how does the observation of something being a category theoretic concept apply to other classes when you compose it. And monoids are very, very common. Functors. So unlike monoids, what we were looking at before, functors are not individual values. It's best to think about them as class templates. So a functor is a class template with a single template parameter. And in addition to this type, you have a callable called map. Okay? And map has the following properties. Map takes in a function as its first argument, let's say from A to B, and it takes in a functor as its second argument. So let's say it's a functor of type A. And what it returns is a functor of type B. So there are different rules associated with this. If you take in an identity function, so a function that always returns this argument as the first argument of the function that you pass into map, that will not change the functor that you pass in as the second argument, because it returns the new functor. It also has some composition rules to make sure that applying a function to a functor, calling map 2 times with 2 different functions, is the same thing as composing the functions first and then calling map of that. But let's build up some kind of intuition for functors. Functors are a lot like containers. Map applies a function to the thing in the container, resulting in a new container of the transformed values. Transform, for example, if you're familiar with that standard algorithm, is like map, but for containers. And the laws provide these reasonable rules for map composition. So, stud vector is a functor. What happens what is the map function defined for stud vector? So map takes in a function, let's say from t to u, and we have a stud vector of u as the second argument of map. What does it do? It creates a new vector for the return value, and that new return value just applies f to all the values in the input parameter. Okay? So again, we're just transforming the values inside of the vector. That's an intuition for vector as a functor. What about stud optional? Is stud optional a functor? What do you think?
Yes, it is.
It is, indeed. And what would its map function look like?
If the optional is empty, return empty, but with the result type. If it has a value, then apply f to the value and wrap that as an optional.
Yes, exactly. Map takes in a function and an optional, and if the optional is none, then it returns a none optional of the transformed type. But if it has a value inside the optional, then it returns a new stud optional value by applying the function to the thing inside the optional that was part of the parameter. Exactly right. What about stud pair? Is stud pair a functor?
Seems like it should be somehow.
Yes, it does indeed seem like stud pair should be a functor. But remember that functors have one template argument which is changing. So with the case of stud pair, what we want to do is take that first template argument, or the second, depending on how you define your map function, and fix it. So the first parameter in a pair doesn't change, or the first value in a pair doesn't change, and the function is applied to the second part of the pair. What about stud function? Is stud function a functor? And it turns out stud function can be a functor if you fix all the parameters of your stud function so that every single function has a fixed set of parameters, and the result of the stud function is that changing type. So you build a new function which transforms the result of the old function. And this is what a map function would look like for a stud function functor. Functors allow for transformations within the type. Each map strips away one layer of your data type. If you're working with a stud vector, you can strip away the vector part of it by using map to get to the thing on the inside. So say you have a std vector of std optional of int and want to get strings for each int. Look at this function and how it's defined. So f1, all it does is it converts an int into a string. f2 uses the map function to convert an optional int into an optional string. And then f3 converts a vector of optional int to a vector of optional string. So you see how we're just building these maps, and each map subsequently gets you to the innermost thing. That is how you can compose various functors of functors of functors and get to the thing on the inside. It's a very powerful composition. Now let's take a look at applicative functors. An applicative functor is a functor with two extra operations, pure and apply. Now, pure and apply have the following rules, but basically pure, the way you can think about it, is a way for you to create a new applicative based on a plain value. So let's say optional is an applicative functor, which we'll find out it is in a minute. If you call pure of 3, you're going to get an optional of int. Apply, this is something that applies a applicative of a function to an applicative. So remember how map, you took just a plain old function from A to B and you applied it to the functor of A to get the functor of B. The difference between that and apply is that apply takes an applicative of the functor and applies it to an applicative value to get a new applicative value. Now we'll look at some examples of this to make it more concrete in a second here. Now, applicative functors have a bunch of laws, and I'm just showing them here to you for your own interest. I'm not going to go over these laws. It does what you would expect it to do if you try to think about what would be the natural laws for an applicative functor. Now, the intuition behind applicative functors, as I mentioned, pure wraps a value into a container, apply applies the contained function to a contained value to get a contained result. And if you think about it, apply can be extended to n-argument functions by doing some additional work. You can base an n-argument apply on a single argument apply. I'll let you think about that as an exercise. So the std optional applicative functor. So pure for optional looks like this, which is of course no surprise. You basically take the value, you put it into an optional. Now what about the apply function? So the apply function, if you think about it, you have the applicative of the function and you have the applicative of the value. So you have an optional function and an optional value. If they both happen to have a value, the optionals is not none in either case, then you apply the thing on the inside of the function argument to the thing on the inside of the value argument, and then wrap that into an optional. If either of them happen to be null, then you just return null. How could this be interesting? Consider this snippet of code. Here we have optional double of A equals some computation, optional double of B equals some other computation, optional value C, you apply plus to the optional double of A and the optional double B, and then D you apply negate to the optional value C. What's going on here? Let's say A is null. What is D going to be? Null. Let's say A isn't null, but maybe B or C turns out to be null. Or actually, let's say B turns out to be null. Well, then the answer would be null. So here what we're seeing is that if you think of null as being an error condition, is a way for us to propagate errors throughout a program. And this isn't the first time this has been discovered. It was discovered a long time ago that applicative functors have this kind of error propagation behavior when you use them with std optional. Interesting stuff. What about std vector? Is std vector an applicative functor? Well, is it a functor? Well, we know that it's a functor. We know what map is for a std vector. What about pure? Well, pure for a std vector could very easily be just create a vector with one element in it of that value. That makes complete sense. What about apply, though? You've got a vector of functions and a vector of values. What can you do?
Apply every function to every value, and you put the result in a vector.
Exactly right. You can apply each function to each different value. For function 1, you apply it to all the different values. For function 2, you apply it to all the different values, and so on until you compute a vector of all the results of all the functions applied to all the values. So what is this? What is this model? Well, think about it. Let's look at this code snippet here. Here we have a vector of doubles A and a vector of doubles B. And what we do is we apply stood plus to A and B. And of course, we're doing the n argument version of apply here. What you get are all the different possible ways to add vectors of A and vectors of B. This is non-determinism. The applicative functor for stood vector models non-determinism. Now, there are a lot of different applicative functors. Stood future is one. Continuations, exception style errors, behaviors and functional reactive programming, of which I'd love to speak more about that one time, or parsers, etc. So functors apply all over the place and are a very key, interesting example. Now let's take a look at parser applicative functors. These are a very interesting use case of applicative functors. The idea here is to be able to build an interface for our parser library and utilize category theoretic concepts as a means for us to build a very powerful parser and give us that minimal set of operations that we want to have, of which you can build everything out of. So, what are the fundamental operations for a parser? So, we'll start by defining our type, parser of T. It's just a stood-in parser that parses into type T, let's say. This is simplifying. In reality, you probably wouldn't want to hard code it to be stdin, but for our purposes, this is just fine. So if P has a type parser of T, P.read tries to parse stood-in. If it succeeds, it returns type T. Otherwise, it throws an exception. You probably want to do something other than throw an exception for your error handling, but again, for simplification, we're just going to do it like this. Now, this particular parser is implemented by having a collection, a vector of chars, which this parser knows that it can parse based on these chars. This will help us with composition later. So if you say, your parser can read, is only valid, if it begins with the letter A, then this vector of chars will have the single value A in it. And it also has a Boolean, which just tells you whether or not this parser consumes nothing. If it consumes nothing at all, then this Boolean will be true. And then, of course, you have this stood function in there, the function which actually does the reading. So in our case, the function has no parameters and just returns the value of type T. All right, that's our type. We're going to create some friend functions here. One is a parser which reads a single character from stood in, any character. Okay, so we just call that char P, and it returns a parser of char. We also have a char P which takes a particular character as input and returns a parser. So this is a parser that if it reads in that character, then it's successful. If that character is not found in the input, then it will not actually parse it properly. And then we have an either function here. So either, what it does is it takes in a parser of type A and a parser of type A, so two parser of type A's as parameters, and produces a parser of type A as a result. And what happens is if LHS, that first parameter there, fails to read for some reason, then it will use RHS. All right, makes sense. So it's using either LHS or RHS will be just fine. And then finally, we have 0 or more. So this is a primitive here that says it will read 0 or more values of type A. Okay, so that way, if the 0 or more, it takes in a parser of type A and returns a parser of a vector of A's by just reading as many A's as possible. Let's see how either would be implemented. Either here, it takes in, as I mentioned before, a parser of type A and another parser of type A. Consumes nothing is only true if LHS consumes nothing. Because if LHS consumes nothing, then it's just trivial. It's always LHS, and that's the end of it. Now the start character here, it will append the start characters from the left-hand side to the start characters of the right-hand side. And that'll be the start characters that are valid for the either of the two different parsers. Now, what about reader? What happens with reader? It reads one character from std_in. It tries to see if that left-hand side parser can support that character. If it does, then it just returns left-hand side.read. Otherwise, it returns right-hand side.read. And then overall, then we take this combined function and we return the result. What about pure? So here we need to be able to create a parser t out of a value t. Pure in this case would be a way for us to just say it always succeeds, so consumes nothing is true, and produces a value, this particular value that you pass into the success p function. Note we didn't call this pure. We called it success p, going back to the idea that you want to make sure that you provide a vocabulary naming that makes sense for your domain, even though you happen to be pure under the hood, using these category theoretic concepts. What about apply? We know that this is an applicative functor, so basically because I told you, but how does apply work? Apply takes in a parser of a function, right? And it takes in a parser of a value, applies the parser of the function, the inside of that parsed function to the inside of the parsed value. Even though nothing's actually been parsed yet, we can still compose these things together. Consumes nothing would only happen if the function parser consumes nothing and the t parser consumes nothing. Now let's say the function parser consumes nothing. So the start character is going to be equal to the value parser start characters, right? Otherwise, it's the start values is going to be the function parser start characters. What about the reader method? So what happens is we call the function parser read to get that function, and we call the value parser.read to get the value and return f of t. And then finally, we return the result. Okay, pretty straightforward. You may not know how we would use apply. You may not know how you use pure, but considering, let's see where this takes us, considering it matches this type theoretic concept. So it turns out that we're done. That everything else that you would need out of this parser can be built on these pieces. Let's take a look at digit p. So here we want to have a parser which parses a digit. So first we create a lambda function which converts a character into an actual number. No problem there. And then we want to be able to parse in the individual characters. So we have char p0, char p1, and so on and so forth, all the way into char p9. All right? We use either to be able to say that any of these individual parsers work. And then we use apply to convert that parser so that either parser, remember, is going to return a parser of char. We change that into a parser of int. So we're just taking these fundamental pieces and applying them together, and we're able to build out a digit parser. Now, what if we want to have an int parser? We can use 0 or more digit parsers, and so on and so forth. There's even ways for you to be able to take two parsers and say, hey, this is a parser of a pair from A to B by getting a parser of A and a parser of B. You can use apply for that. And putting all this together, if you want to have two ints separated by a space, you can take that function that we just used and just make parse an int, parse a space, parse another int. So are you starting to see how you can build these powerful, powerful libraries by using these fundamental operations? That's the idea. Let's review this. Monoids. What are monoids good for? These are highly parallel patterns. In fact, it's a generalized version of MapReduce. If you find that the domain you're working on happens to model a monoid, then you know you can apply a MapReduce kind of like system to work this in extremely parallel terms. What about functors? Functors, you do things to the stuff inside. And you can thread functors of functors of functors to get to the thing on the inside. A very powerful abstraction. And applicative functors. This is a way for you to put stuff inside, and the stuff inside can do things to the stuff on the inside. In other words, the apply function. Now we look at monads. Now a monad is an applicative functor with one extra operation called join. So join takes in a monad of t and produces a monad of t. And that's it. A monad is simply an applicative functor with a join operation. Now, there are monad laws, and it's a bit more complex to express these in C++, so I'm not going to throw them on the screen here, but I will say, please go to this link, the category theory webpage there, and you'll be able to understand how this works for Haskell, and you could intuit how these monad laws would apply for C++. Now, what would join look like for stood optional? Join, remember, it takes in the monad of a monad of T, so in this case, it would be an optional of T. Join, what it will do is take an optional of T and build an optional of a T out of it. The implementation is probably exactly what you would expect it to do. Pretty simple. What about other monads? There's stood vector. There's a parser monad. Now, the parser applicative functor that we made before is different than the parser monad. Our parser doesn't have the ability, as an model as an applicative functor, to be able to start with a parser, parse a parser, and then apply the parsed parser to the input, right? So imagine, a parser where the first thing it does is it parses the language for the rest, parses the parser that's supposed to apply to the rest of the language of the input. Applicative functor parsers can't do that, but monad parsers are, so that gives you that extra power. Functions with a single parameter of type A actually are also a monad. So what's the big deal? Who cares about monads? It just seems like it adds one thing to applicative functors. Well, this bind operation. So I talked about it way back at the beginning. Don't expose your thing and call it monadic bind. Well, the monadic bind operation is defined in terms of other operations. So for a given monad of T, in order to be able to construct a bind, you use pure, apply, and join. Usually, for bind, you want it to be an operator overload. Let's use the right shift operator. Here we have an optional of int getInt function. And here we use the monadic bind to be able to start with getInt. You have some kind of syntax. GetInt, you have some kind of other syntax. GetInt, you have another kind of syntax, and you call pure of A plus B plus C. If you indent this a little bit differently, it looks like this. Now, if you squint, you might see something like this, which, if you cross your eyes, looks like this. In other words, this looks a lot like imperative computation. And that was the original reason why monads got so popular in the first place, is because it looks like imperative computations. And that was a really big deal for Haskell. But what about us? Does it do anything for us in C++? Well, what monads allow you to do is express different models of computation within C++. Stood vector gives a language with non-determinism. Stood optional provides a language with error fall through. There are continuation languages. It also allows you to provide more control over computation. You could take a computation which is expressed in monad form and serialize the computation itself, and then deserialize it and use it. You can have a command pattern embedded language. It is also extremely interesting for imperative template metaprogramming. So let's wrap this up. The first thing to note is this is just the beginning. There are more interesting patterns: semigroup, category, arrow, comonad. All of these can be used to enhance your design skills. Now, I will probably do a subsequent talk at one of these conferences at some point to talk about more examples of these things. But here is your base knowledge of very common repeated software patterns in functional design. Now that we've finished, let's go and take some questions. Cool, thank you. Glad you guys liked it. Let me go to some of these questions here in the QA section. What did you bribe those kids with to put up with this? They were good sports, you know. They were happy to join in. The kids are a lot of fun. You know, if you search for Sankel Family Band on YouTube, you'll be able to see the kids in action, like actually playing music. Like we've made some YouTube videos before as a family, and it was a lot of fun. So yeah, they were totally good sports with this. Next question is, what is your presentation setup in brief? Okay, so I basically had a cell phone on a tripod, And I saw someone mention like, oh, it's a green screen. I wish I had a green screen. It was just the ugly color of my wall that was behind me. And then I recorded that, and then I recorded with the kids in a different room actually. And then we put it all together with Adobe Premiere and just added all the text effects and things like that. It was slow at the beginning, but by the end, I got pretty fast with it. It was neat. It was a good experience. Next comment is from Victor is we want to see the blooper reel. That would be hilarious. There are some pretty funny things. At some point, maybe I'll put this together and throw on the YouTube the blooper reel. It was like interruptions. So you saw all my kids there, except there was like the smallest kid. We did not invite into that part of it, but he invited himself a couple times. So that would be pretty funny. Okay. What is the difference between, oh, that one disappeared. Is it possible to create C++ 20 concepts for monad, monoid, etc.? For sure, you'd be able to create one for monoid. In terms of monad, I'm not sure that concepts are powerful enough to express that. They may be. So I haven't thought deeply about it. It's a good question. But it kind of boils down to, what do you really want to expose these as they are to your user? So from like a software engineering standpoint, if you have a bunch of users for your software, it's probably not going to be useful for them that they have a unified way to talk about Monadic Bind. But if you're experimenting, you're having fun, and your folks that you're working with have a lot of experience with these kinds of concepts, then it might be useful. Then they can just say, hey, we'll use mappend if you want to like squash the vector or any kind of container of monoids. Next question. Let's see. How bad do the diagnostics and stack traces get when debugging these patterns expressed in C++? So I think that it's similar to any kind of metaprogramming like kind of design that you're going to do. If you just do a kind of default setup and you don't actually think about diagnostics, then you're going to get like just incomprehensible error messages. But you can go in and make sure that you get the kind of like errors that you want to have, so like give like little helpful hints to the user as to what could possibly be going wrong. So that's more of just template metaprogramming kind of design as a way to kind of like improve error messages. So it's not different than any other kind of complex template kind of shenanigans you'd do. Okay, let's see, next question here. Many people bounce off of Haskell category theory. Do you have a recommendation for people who want to learn it but bounce off? I'm not sure what is meant by bounce off. So I'm not really sure how to answer that question. Maybe Connor, if you can state it in a different way or clarify what you mean by bounce off, then we can. I'll give that one another attempt. Let's see. Next question is. Oh, questions are kind of coming in and disappear. Do you think that the lack of custom syntax in C++ for building monadic expression can make the use of monads too impractical? Excuse me. I think that it does hurt in a lot of respects. If you want to be able to express something in monadic form, it'd be really nice to have do notation, which is like in Haskell, you have a special notation that you can use for monadic computations. In terms of whether or not there is a strong enough use case for monads in C++ that we'd want to add that to the language, I don't know just yet. You can get away with quite a bit with just function syntax, like making an embedded domain specific language, kind of like as we saw with the Applicative Functor parser library. I see. What is the difference between a monoid and a group? And then it seems like an answer below it. A group has an inverse for each element. The next question is, I feel like I struggle with the terminology of monoids, monads, etc., yet understand some of the concepts intuitively. How would you recommend I go about deepening my understanding of these concepts? I think that what really helped me a lot was to actually try to implement stuff. Take stood optional or something along these lines and just try to implement all the different operations for it. And then take like a stood function and implement all the different operations for that. And if you just do this over and over and over again, you start to build the intuition. Monads in particular are like a very difficult thing for folks to internalize in their heads. And like one of the common memes among Haskell people is that you learn monads and then it just becomes simple and you just like understand it, and then you want to tell everybody about it. Like, monads are so simple, and you explain it, and it's like you're speaking Martian to people, because there seems to be no way to get to that end state to where you understand it without going through this journey of messing around with it and learning it and working it over and over in your head until it finally clicks. Good question. Let's see. Oh, the clarification on BounceOff. BounceOff, find it too difficult to learn or find it unfamiliar. AKA, many people give up on learning Haskell in their first few attempts. Yeah, that's true about any endeavor that's worth doing, right? If it was easy, everybody would have done it already. But it is something that you have to master in order to be able to work with it. There's no royal road to math, as they say. And the same is true for some of this category theory. Category theory is advanced math. But we do have a road, may not be a royal road, by trying to implement these things in C++ and be able to build our understanding about it. Let's see. If you could magically extend the C++ standard to better support functional programming, what would I add? Well, that would definitely have to be pattern matching, right? So pattern matching, which is not related to category theoretic concepts, is just a simple way for you to make use of algebraic data types like variant. But variant right now is kind of cumbersome to use, especially when you compare it to some of the functional programming languages. So having pattern matching in the language and also first-class support for variants would definitely be high on my list, and are high on my list. And you can see my papers that I've submitted to ISO on that behalf. And the pattern matching one, it is something we are trying very, very hard to target for C++ 23, and I'm just a co-author on that. There are several authors on that paper. The pattern matching would be up there because that is useful right away by everyday programmers, and it would be in every single CPP file if it were used. What is an example that's not a functor? So like an int would not be a functor. Something that doesn't have a map operation. Anything that might, the key thing about a functor is that if you pass in the identity function, that you can't mess up your object, change it. So any kind of map operation which doesn't do that wouldn't have that property. It's hard to come up with a juicy example where it's like, oh, you'd think this would be a functor, but it's actually not. Functors are very, very common, and it's kind of hard to make something which you can apply a function to that wouldn't be a functor. But you can come up with something. Do you think that someone could use these tools using template metaprogramming, implement map, pure, join, apply in order to use it more efficiently? Someone could definitely use these tools with template metaprogramming as a means to make template metaprogramming feel less functional in nature. Right now, a lot of the template metaprogramming tools, they're not really imperative much. It feels more like you're writing in a purely functional language. So monads in particular would allow you to make a embedded domain-specific language for template metaprogramming that feels more like imperative programming. Of course, it's not going to feel as great as like first-class imperative template metaprogramming, which is something that we're trying to do in the standardization process to make template metaprogramming easier. But it can, in the meantime, provide a means to make a more imperative feel to your template metaprograms. Okay, next question is, how do you walk the line of exposing too many members that are in terms of the most essential ones and being too obscure in your interface, locking inexperienced programmers out of using it? So that's a really good question. And that is an art form, right? There's no like mathematical answer to that. So one way of designing interfaces is you put in your public interface only the minimal set of extremely powerful generic members, and then put everything else as a free function or in a different file as a utility. All right, so that's one way of doing it, but it's not the most user-friendly way of doing it. What a user wants to see right away are the most common operations. So whatever is going to be most common, depending on how you expect your users to actually use your library. In my opinion, I like interfaces that expose those like front and center. So elevate it to the level of a member function, just because that's where they're going to go looking for it. But yeah, you have to look at each individual case and get it looked at by many different people, many different stakeholders, especially people who are not the author, and get that feedback and incorporate that into the design in order to come up with a design that's going to be palatable and extremely popular. Okay, next question. What would you say is a canonical first example for comonads? I can't really think of what would be a good canonical first example of comonads off the top of my head. But for a future talk, when I take a look at that, crack it open and look at all the different examples for comonads and try to think of one that would be a good introductory case, I can try doing that. Yeah, comonads are a bit more obscure in their functionality than even monads. So you have to build it up a little bit, but it would be a challenge to find a good first example, for sure. I'm still a bit confused on how monads are still considered purity. Is it because the fact we're hiding the impure parts behind the monad type? I'm specifically talking about monads like IO or parser. Good question. So the reason that monads can be considered in a certain sense pure is that the way that you think about them, like in Haskell, for example, is an IO monad is like a piece of computation that is a primitive thing. And that we're just saying is like some other universe. Connecting these different pieces together, like being able to say, hey, read an int and then read another int and then put them together and read the result. All the computation which combines monads, which you can kind of think of it as kind of like overloading the semicolon operator, that part is pure functions, right? So you're composing these impure things in a pure way. And that's why monads are considered, in that sense, pure. Would it be difficult to get this sort of parser efficient enough to compete in runtime performance with procedural equivalents? No, it would not, especially the applicative version of the parser, to where every parser is associated with the initial character that it can read. That actually makes it very efficient. That either operation, for example, when it gets to when you're actually parsing something and it gets to that, it's just basically a switch over a bunch of different statements there. Now, there are things that you can do to make it even more efficient and complicate the code a little bit more, but there are definitely some high performance parsers that have been built in this way that are competitive with things done in other ways, for sure. All right, Bartosz started down this path in C++, but soon ran out of steam and switched to Haskell for good. Do you think these concepts are too unnatural for a language as C++, e.g. too verbose of a syntax? So I can't speak for Bartosz, but one of the things that's extremely attractive about these is when you get the sense of the purity and the beauty behind these mathematical structures, you tend to fall in love with it and make that your life and make that your dream. And a lot of functional programmers are in exactly this boat. They love messing with it. They love the math. They love the abstract theory, and they love living in that world. And that is totally legit. Personally, I'm a software engineer, which means all these things are useful to me. I do appreciate the beauty, but these are useful to me in the context of creating software that people are actually going to use and is going to actually impact the world. And most of us who are writing C++ software, our software is primarily to be used and to impact the world. And so in order to do that, we have to make sure that we have public interfaces that work with the people around us. So yeah, I personally, I can appreciate the beauty of going off the deep end and, for example, programming in Agda. I love Agda as like a programming language, and it takes Haskell to the absolute next level. But it's just not practical. And when you're trying to solve real world problems, practicality is at the foremost of it. Could you name some naming examples for monadic binds? So one of the most common things to call monadic bind is then. So if you look at many implementations of futures, not the standard future, but like maybe Boost future, their monadic bind operation is called .then. So you have like a.then, and then you pass in a function of that, then .then. So that's probably the most common naming. It's not like some symbols that I've seen for monadic bind in C++. Good question. Scala has monads. Does C++ go in that direction? So C++ is an engineer's language, right? And so there are a lot of possibilities of things that we can add to C++. The question is not what are they and in what direction do we want to go in. The question is, what is the highest priority thing right now? So for C++, like my priorities, adding first-class monad support is certainly an interesting thing and would make the language better, but it's definitely not at my highest priority list. I'd rather see things like pattern matching and reflection and the kinds of things that we're actually working on right now to try to add into the language. It's lower down there. You know, it's definitely on the list of things, but I think we've got other fish to fry, like having a networking library in C++. I mean, it's kind of an embarrassment that we don't have one. So I would just kind of prioritize it lower than the other things that we could possibly do with C++ language. Next comment is many functional patterns in C++ are handicapped by the lack of lazy evaluation. Any thought on lazy eval? So lazy eval would be interesting and definitely would help out with some of these functional patterns. And there's actually been some proposals along these lines to be able to add lazy eval. I think that probably the biggest impediment to getting lazy eval in C++ is compelling use cases that make people say, this is more important than the other stuff that we're doing. And when we see more of these things, then I think that it could become a reality that we want to add lazy evaluation. But if we do bite off lazy evaluation, it adds a huge amount of complexity. Lazy evaluation in Haskell is not so bad because it's a pure language. But we don't have a pure language, so we have the complexity of it being both pure with lazy evaluation and impure with non-lazy evaluation. And that's another concept that our engineers are going to have to think about all the time. So we got to be aware of the cost of taxing our developers with more complexity in this language. Okay, cool. I think that all the questions are at this point answered. I'd be happy to hang around if anybody else has any other questions. Otherwise, thank you. Appreciate it.